Hello, this is section 5.8 and it's about the difference in sample means. Here we go. So remember from last time, so some statistics memories here, that when we're talking about the sampling distribution of a sample mean, for one population where we take a sample repeatedly and we calculate the average from that sample, that when we're talking about shape, we have that if the population is normal, then the sampling distribution will be approximately normal. And if the population shape is unknown, then you need a really large sample. And usually we say greater than or equal to 30 or more for your sampling distribution to also be approximately normal. So we're talking about shape of a sampling distribution for one population and one sample mean. We want our either our population to be approximately normal or for the sample size to be large in order for that sampling distribution to be approximately normal. We also have on our formula sheet that the variable for the sampling distribution of a sample mean is x bar, that the mean of the sampling distribution is the same as the mean of the population, and that the standard deviation of the sampling distribution is related to sample size, and it's sigma over the square root of n. And the larger the n value, the smaller the variation is going to be in your sampling distribution. And those are on your formula sheet. You need to know those are there, but you don't have to be able to memorize those. And then finally, we talked about if you wanted to find a probability of a mean, so not the probability of a single value, but the probability of a mean. For example, find the probability that the mean pregnancy length for 6 women exceeds 270 days. You start off by thinking, okay, is it one pregnancy greater than 70? Nope, it's the average, so it's an x bar probability greater than 270. And then you would find the mean and the standard deviation. You'd confirm that the sample shape is approximately normal. And then you set up a normal distribution with those parameters identified with the boundary and the direction, and use your calculator to find that probability using that norm CDF. Okay, so today is very, very similar. So to start off, a problem might look something like this. Let me see if I can move my face here. All right, so the distribution of height for 4-year-old girls is approximately normally distributed with a mean of 100.3 centimeters and a standard deviation of 5.2 centimeters. The distribution of height for 4-year-old boys is approximately normally distributed with a mean of 102.3 centimeters and a standard deviation of 4.7 centimeters. Suppose we take a simple random sample of size 10 from each population, that would be from the 4-year-old girls and the 4-year-old boys, and calculate the mean height from each. What's the probability that the difference in sample means is less than 0? All right, so one thing you should notice here is that this is a problem referring to two populations. We've got two groups of people here, 4-year-old girls, 4-year-old boys. Okay, two groups of people as opposed to just one group of people. Okay, so when we go to work our way through this, we should try to identify all those pieces. So group 1, I read through, I see it's all the 4-year-old girls. And the height, it says, is an approximately normal distribution. The mean is 100.3 and the standard deviation is 5.2. And we're planning on taking a simple random sample of 10. And then I look at group 2, and again, it says that this would be the boys. This would be the height is approximately normal according to the problem. There's the mean of 102.3, standard deviation of 4.7. And again, we're going to take a simple random sample of size 10. All right, so symbolically, when we look at these, group 1, we want to label all these with the correct variable. So that mean is going to be a mu sub 1. That standard deviation is going to be a sigma sub 1 because those are for the population. That's for all the 4-year-old girls. Sample size is N1. And then when we talk about the sample mean from that sample, that's going to be an X bar 1. Okay, so just like with proportions when we work with two groups, we're going to use these subscripts to help us keep all the data appropriately defined. Okay, and then the same thing for group 2, we're going to have mu2, which always makes me laugh because it makes me think of a Pokemon character, but you know, whatever. So we have mu2, who is 102.3. The sigma 2 is 4.7. Okay, those are our population parameters. And then our sample size 2 is 10. And when we refer to the sample mean, we're going to call that X bar 2. So when we're talking about shape, it's very similar to last time. Okay, so we have these statements from the College Board website here, and it says the sampling distribution for the difference in sample means, which is X bar 1 minus X bar 2, can be modeled with a normal distribution if the two population distributions are normal. So with one mean, if the population is normal, the sampling distribution is normal. For the difference of two means, if both populations are normal, then the sampling distribution of the difference will also be approximately normal. And if it's not, then you have the central limit theorem comes into play as well. And so if you can't say the populations are approximately normal, you can still get a normal distribution as long as both sample sizes are large enough. In other words, as both sample sizes are bigger than 30. Excuse me. So for our group, both of the populations were approximately normal, which means that our sampling distribution shape is also approximately normal. And just caution, 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 oh my goodness, please. The central limit theorem, this greater than or equal to 30 thing, is only good for means. It is never good for proportions. So remember, if you're trying to confirm normality in a proportions problem, you have to check the n times p and the n times 1 minus p to see if they're greater than or equal to 10. All right, so when we talk about center, this is also on your formula sheet. So if you look down the back of your formula sheet, you're going to see for two populations, x bar 1 minus x bar 2 is the variable, and the mean and the difference of the two sample means distribution is just mu1 minus mu2. So you're going to see that this is very familiar to the proportions where it was p1 minus p2. So the mean of the sampling distribution is the difference of the means of the two population distributions. So in our example, our mu1 was 100.3 and our mu2 was 100.2.3. We subtract, we get a mean of negative 2 centimeters. Now don't distress yourself that that's negative. It's the difference, and all this is saying is that population 2 had a larger average than population 1 did. Or in other words, on average, the boys were taller than the girls were for the population. Okay, for the spread, we talk about standard deviation, and you'll notice that this formula over here that I've got circled on the formula sheet is a little bit different. It's got that square root. Notice that it's sigma 1 squared over n1 and sigma 2 squared over n2, and that has to do with the fact that we're adding the variances. Okay, so one thing to keep in mind when we were talking about means that with one population, that if your sample size is less than 10% of your population size, there's no real big difference between sampling with and without replacement. So in our case, if we've got two samples, we need to make sure both samples are less than 10% of the population if we're sampling without replacement. Okay, so in our example, both sample sizes were 10, and I think it's very reasonable that 10 is less than 10% of all 4-year-old girls and all 4-year-old boys. So both those are reasonable, which gives us permission to pop into this standard deviation formula. So I took my square root, and I've got the first standard deviation squared divided by 10, plus the second standard deviation squared divided by 10. Now when you do this in your calculator, don't distress. You're just going to type it in like a straight line. So you're going to go the square root, and you're going to do 5.2, and you have a little button that says x squared. If you hit that, it'll just put a little square on that number. Divided by 10 plus 4.7 squared divided by 10. When you do this and hit enter, it's going to come out just like we typed it above and give you that 2.22 centimeters approximately. Okay. All right. So the question that was asked in this problem says, what is the probability that the difference in sample means is less than 0? What's the probability that the difference in sample means is less than 0? So that's like saying the probability that x bar 1 minus x bar 2 is less than or equal to 0. So what do we know? We know that both populations were normal, so the sampling distribution is normal. We know that the mean is -2. We know the standard deviation is 2.22. That gives us the ability to draw that picture we've been drawing. So I'm going to draw the curve. I'm going to label the x bar 1 minus x bar 2 difference of sample means on my x-axis. Okay, mean of -2, standard deviation 2.22. That puts the mean of -2 in the middle. It's going to put 0 over here on the right, and we want less than 0. Okay, so I'm just going to norm CDF in my calculator from -infinity to 0 all the way up with a mean of -2, standard deviation of 2.22. We get about 82% here for our final answer. Okay, all right, so here's another example. A large coffee company serves thousands of cups of coffee each day. Due to recent quality control checks, they suspect that the night shift may be overfilling the cups. Suppose that, on average, coffee cups from day shift are filled with 8 ounces with a standard deviation of 1 ounce, and coffee cups from night shift are filled to 8.5 ounces with a standard deviation of 1.85. And let's assume that the shifts are independent of each other. Okay, so the quality control team takes a simple random sample of 40 coffee pours from each shift and they calculate the mean fill amount in ounce and calculate the difference between the sample means. And I want to know, find the probability that the difference in sample means is greater than 1 ounce. In other words, are they off by more than 1 ounce of each other? Because that might be concerning. All right, so I'm going to go through, I'm going to pick out my problem. So I see population 1, there's 2 groups here. We've got day shift and night shift. So this is a 2 population kind of problem. So population 1, let's call that day shift. It says they have a mean of 8 ounces, that's going to be a mu1, and a standard deviation of 1 ounce, that's sigma 1. And they're going to take a simple random sample of size 40. So N1 is 40. Population 2 is going to be the night shift. It's stated that their mean, so it's going to be mu2, is 8.5, and sigma 2 is going to be 1.85. They're also taking a sample of 40. Okay, so I've got all my data kind of picked out of the problem, and I'm trying to find the probability that the difference in sample means x bar 1 minus x bar 2 is greater than 1 ounce. Now remember, if you struggle with that notation, that x bar 1 minus x bar 2, that's on your formula sheet in that variable right there. So if you're curious of what should the variable be that I use on these problems, try to find where it says 2 populations and you can copy it straight from there. All right, so I'm looking for this probability, so let's check the shapes. Now, it doesn't say anything at all in here about population shape. Population shape, unknown. I have no idea. Okay, so I can't use that. So I'm going to have to count on, are the sample sizes large enough? So I'm going to check. N1 and N2 are both 40, which are greater than or equal to 30. That means they're large enough, because by the central limit theorem, as long as your sample size is large enough, bigger than 30, then your sampling distribution is going to be approximately normal. All right, so I know the sampling distribution is approximately normal. Next thing I'm going to do is I'm going to find the mean. All right, so for 2 populations, I know that the mean of x bar 1 minus x bar 2 is going to be mu1 minus mu2. Okay, so I'm going to take 8, which is mu1, minus 8.5, which is mu2, and I get negative 0.5. Now again, this number can be positive or negative. It's not that big of a deal because it depends on what direction you subtract them. So as long as you're always consistent with all your 1s and all your 2s, the mean could be a positive or a negative number depending on that. Okay, so there's my mean. Next thing I need is the standard deviation. I've got this handy dandy formula here, but remember, this only works if I got less than 10% of the population. So I'm going to check, is 40 less than or equal to 10% of all pours for the day shift? And is 40 less than 10% of all pours for the night shift? And I think that's probably reasonable. Okay, so I'm just going to say reasonable, moving on. So I'm going to compute this in my calculator. I'm going to do square root of standard deviation squared, 1 squared over 40, plus standard deviation squared, 1.85 squared over 40, and then a square root, and I end up with about 0.333. All right, so I'm looking for this probability. I know the distribution's normal. I have the mean. I have the standard deviation. I'm ready to draw a picture. Okay, so I've got my normal curve. I've got it labeled, mean, standard deviation. If the mean is negative 0.5, then 1's going to be over here to the right of that somewhere. Okay, and I'm looking for greater than 1, so we want the right side. Now you little norm CDF, 1 to infinity. And remember in your calculator, you may need to type in like 10 to the 99th power for infinity. Since it doesn't default there. I'm going to put in my mean and standard deviation, and I ended with 0.000003 when I did this. So to 3 decimal places, we're talking about 0. Okay. Which also means that I didn't draw this picture very well. That must be very much farther over to the right. All right, so essentially 0, sometimes we would say. All right, so that's about it. I mean, it's very similar to before. So let's just kind of compare. So if I've got 1 population, I know that the sampling distribution is going to be normal if the population is normal or if the sample size is large. For 2, I need either both populations to be normal or both sample sizes to be large enough to act that central limit theorem. Okay, so for 1 population or 2 populations, we're looking for either, for the sample mean, for the sampling distribution, we're looking at either knowing what the population looks like and knowing that it's normal, okay, or we're looking for those sample sizes to be at least 30. And remember, this only works for means. If you're talking about proportions, you have to check the NPs and the N times 1 minus P's for those. Now, when we're talking about means, for 1 population, the mean of the population is the same as the mean of the sampling distribution. And for the sampling distributions for the difference, you're going to find the difference of the 2 population means. For standard deviation, in order to use those formulas accurately, you need less than 10% of your sample, less than 10% of your population. So we're talking about 1 sample, that 1 sample has to be less than 10% of your population. If you're talking about taking 2 samples, then both samples need to be less than 10% of your population, and that lets you calculate those standard deviation formulas. Now, these are not have to be memorized, but you do need to know where they are on the formula sheet. Anytime you're finding the sampling distribution for a sample mean, make sure you're doing that sigma divided by square root of n. And anytime you've got two sample means, you've got this square root. And be really careful because those are squares in the numerator there, okay? And so it's a square root of the whole thing and just this, instead of the square root of just the bottom. So be very careful that you sub into that formula correctly, okay? And then finally, if you are talking about are finding probabilities, the probability calculation is pretty much the same for both of these. Once you've determined it's normal and you found the mean and you found the standard deviation, you're going to use norm CDF on a nice shaded curve with boundary and direction and variables labeled, and it's beautiful. Okay, you're going to want to make sure you do that for both and then use your calculator to find those probabilities. All right, and that is it. So good luck and let me know if you have any questions.